Welcome everybody. I would like to present the famous ranked order tournaments paper of Lazear and Rosen. And this is the outline. As you can see, it will be a relatively long presentation, maybe 45 minutes, 1 hour. So I will start to motivate the paper, and then we will have a look at the so-called piece rate scenario. And afterwards, we switch to the tournament. In the beginning, I would like to focus on this picture here. It is a case that we see two participants of a marathon, and in the end, it is a case that one woman is winning, she is winning because she's faster than this lady over there. But what we don't know is whether it's pure luck that this person is winning. Maybe it is a case that the two persons excelled the same amount of effort, but in the end, this lady here was more lucky than this person. We don't know. The only thing we know is that one person was faster than the other. I would like to come up with a kind of scenario analysis with respect to the prize money. What if the purse is equal to 1,000 US dollar? So the sum of the two prize money is equal to 1,000, and we are splitting the prize money 50-50, 500 on rank 1 and 500 on rank 2. In this situation, it is a case that the spread is equal to 0. So the difference between the prize money on the first place and the prize money on the second place is 0, and therefore there is no incentive to run fast, because it is a case that both sportsmen or sportswomen, they know that irrespectively of whether I'm running fast or slow, I will earn 500 US dollar. Only when there is a difference between the prize money on the first rank and the prize money on the second rank, then it will be the case that this will lead to a scenario where the sportsman will excel some effort, because it's a case that only 30 US dollar, this is the amount which both sportsmen have for sure, and the additional 40 US dollar spread incentivates both sportsmen to run fast. Here or there during my presentation, I will stop the topic a little bit, and I will raise multiple choice questions. For example, here, the question is, why is it important that there is a spread between the two prices? Yeah, of course, the right answer is answer number 3. The wage rate W2 can be taken for granted. Only the spread incentivizes the sportsman to excel effort. The first answer is wrong. In case that the prize money is the same, the effort level would be too high and the two sportsmen could not finish the marathon. This is bullshit. Nevertheless, why could the purse, the sum of the prize money, could be important? The prize money could be important because of the fact that in case that you want to have very good sportsmen which show up at the starting line, you need to incentivize them to participate in the race. And therefore, the sum of the prize money could be important. Let's have a look at the structure of the industry. It is the case that the spectator pays some money to the firm. The firm is organizing the tournament, or the firm is organizing the marathon. Afterwards, the firm will pay the worker, the firm will pay the athletes. Afterwards, the athletes will excel effort and create an output, and the firm will sell the output to the spectator. The background of the paper is that it's a labor market paper. And Lazear and Rosen, they asked the question how to best compensate workers. Should it be an hourly wage or a piece rate pay? So how does the principal get the best effort from the agents? This is the overall question of the paper. And then they are asking the central question, what if the principal sets up a competition? The more successful agent should receive the prize money W1, and the less successful agent should receive the prize money W2. Of course, it should be the case that yet W1 is larger than W2. The prize money on the first place should be larger than the prize money on the second place. Furthermore, it is a case that we are looking at a one-shot game, so we are playing the game only once. There is no repetition. We have only two agents. We have two workers, competitors or athletes, which are competing for the first or the second place. So Lazear Rosen are not looking at the case where n is larger than 2. The firm organizes the tournament, the marathon, and the principal and the agents are risk neutral. So the firm and also the two agents are like risk neutral. Furthermore, we assume that the two workers, J and K, they produce an output Q by applying effort M. The more effort, the higher the output, but the process is disturbed by an error term epsilon. So this is highlighted in equation 1. The output Q depends on the effort of the athlete and then also the error term. We can motivate this equation as follows, like normally one worker can produce like 1 unit of output per day, for example, but sometimes the worker is in a flow and can produce more, then epsilon is positive, and sometimes the worker has a hangover and produces less. So on good days, epsilon takes a value of 0, and on bad days, epsilon takes a negative value. On normal days, epsilon will be equal to 0. Furthermore, we also assume that we can only observe Qi. We cannot observe Mi, the effort level, and we cannot observe like the error term. The effort level Mi as well as the error term are unobservable. So the firm and the spectator can only observe the output Qi. This is already something which I mentioned in the beginning. So we know that this person was faster than that person, but we are not able to disentangle like the effort level and this random disturbance epsilon, the good luck or bad luck component. We only observe like the output that this person is faster. Supplying effort is costly. So supplying effort is costly to the individual, and we will model that by looking at the cost function Cm. So cost is a function of effort. This cost function should have the following characteristics. The first derivative with respect to m should be positive. So a higher effort level leads to higher cost. And the second derivative should also be positive, which means that del squared c del m squared is larger than 0, so marginal cost increase. This can be motivated as follows, like you have to exert some effort to run from kilometer 8 to kilometer 9 in a marathon, and you also have to exert effort to run from kilometer 38 to kilometer 39. But of course, this kilometer from 38 to 39 will be harder. It will create more cost because like you have already excelled like a lot of effort before, so it's harder to run this kilometer here compared to that one. So one function which fulfills this characteristics is when Cm is equal to m to the power of 1.5. So the first derivative is definitely positive, and also like the second derivative is positive. So later on in the numerical example, I will work with this specific cost function. So the first scenario we are looking at is a piece rate scenario. I mentioned that the Lazear-Rosen paper is a labor market paper, and therefore they want to look at different scenarios and want to find out what is the best compensation scheme. So the first scenario is a piece rate scenario. So the company pays the worker a piece rate equal to R, and the expected earnings for each worker is given by the following utility function. So the worker is in the end creating the output Q, and this will be compensated by R, and we have to subtract the cost. When we build expectations, it is a case that the expected value of Q is equal to the effort level of M, and hence R times M, this can be regarded as a kind of revenues, and we have to subtract the cost. The first order condition, we have to think about what is under control of the worker, and the worker can determine the effort level. So when we differentiate the utility function with respect to M, we get R minus the first derivative of the cost function. This has to be equal to 0, so that the piece rate has to be equal to the marginal cost. The rate is equal to the marginal cost of the worker. Furthermore, we have to look at the solution for the firm, and the firm is selling the output on the products to the customers at a price of V. So the cost of the firm is given by the labor cost, the compensation for the athletes. Therefore, the profit function is given by V times Q. This is the revenues to the firm, because the firm is selling the output to the spectators, and we have to subtract the labor cost. We can put Q out of brackets, and then we get V minus R times Q. This will be equal to the profit of the firm. One special assumption of the Lazear-Rosen paper is that firms operate in the market structure of perfect competition, so that the profits of the firm are equal to 0 in the long run, and this implies that V is equal to R. So profits only can become 0 if V is equal to R, because Q, the output, will be positive. Under consideration of the optimality condition of the worker, it can be concluded that V is equal to R is equal to marginal cost, so that production and compensation is efficient. The social cost of production is equal to the social return. So Lazear-Rosen have shown in this scenario that a piece rate compensation is socially efficient. But now we will directly jump to the second scenario, which maybe is more interesting, like the compensation in a tournament, where the firm is setting prize money to the first place, W1, and prize money to the second place, W2. So with the probability P, agent J is better than agent K and will receive the higher wage W1. With the probability 1 minus P, agent J is worse than agent K and will receive the lower wage W2. So the utility to the worker stems from the following components. So with the probability P, agent J is the fastest and will receive the high prize money. With the counter probability, the athlete will rank second and will receive the smaller prize money, and then we have to subtract the cost. We can also put P out of brackets. So we have 1P here and a minus PW2 here. So when we write P out of brackets, we get P times W1 minus W2, which is equal to like the spread plus W2 minus the cost of excelling the effort. So like this is the utility for the athlete, and of course we have to talk about P now, like the probability function. Whether agent J wins the tournament or not depends on the relationship between the output of agent J and the output of agent K. So like agent J will win in case that the output of agent J is larger than the output of agent K. But the output depends on the effort level as well as on the luck component. So like we can insert for a Qj, mj plus epsilon j, and for the effort and for the output of agent K, we can insert the effort level of agent K plus the luck component of agent K. We can sort the elements a little bit different. We can put like the m component on the left-hand side and the epsilon component on the right-hand side, and then we receive like the following relationship here. The probability of winning depends on whether like the effort differential is larger than like the luck component. So when we go back to the Lazear-Rosen paper, they define the difference between the two shock components as Xi. And in one teaching note, like Maloney defines the difference between the two shock components as X and refers to this expression as a density of bad luck. This is a very nice expression, therefore, like I'm using this, but we have to answer the question, bad luck for whom? Like it is bad luck for player J, because when agent K receives like a very high epsilon, then the output of player K will be high, because of the fact that he has a high luck component. And hence, the difference, epsilon k minus aj, epsilon j, so the difference implies like bad luck for player j. So when x or xi is very high, it implies bad luck for player j. So player J wins the competition in case that the effort differential is larger than the realized bad luck component. We can use this picture, which also stems from the Maloney teaching note. We have here the winning probability of athlete J, and this is on the vertical axis, and on the horizontal axis we have like the effort differential. In case that the effort differential is equal to 0, then both athletes are excelling like the same amount of effort, and the probability of winning should be like 50% for athlete J. In case that athlete J excels some extra effort, so if mj is higher than mk, then it will be the case that the winning probability will be higher than 50%. So if athlete J excels this amount of effort extra on top, then the light green probability mass will add to the 50% probability mass, and hence the winning probability of athlete J will be higher. So in case that player J pushes his effort level above the effort level of player K, so that like mj is larger than mk, player J will increase the winning probability above 50%, and player J can still win despite some portion of bad luck. What happens if? Like, I would like to ask the question, what happens if player J goes like one step to the right? By how much does the winning probability increases? Of course, like by the height of the probability function. So when we go like one step to the right, then the additional probability which will be covered is given by the height of this probability function. And then, of course, it depends on whether the variability of this probability function is huge, as it is in the blue scenario, or whether it is very small, which is the case in the black scenario. So in the blue scenario, it will be the case like that the additional probability which goes to player J for excelling 1 unit more of effort is relatively small because there is a high variability, and in the black scenario, the additional probability mass is higher. So Lazear-Rosen assumed that the error terms of the production functions are normally distributed. The density of bad luck is then normally distributed with a variance of 2 times the variance of the two error terms, because like each sportsman receives like one error term, therefore the variance is double the variance of the single sportsman. The derivative of the probability function with the effort level m is given by equation 10. So in the end, we have to look at this function g. It is important to make clear that you understand this assumption. The two agents are model symmetric. So in the equilibrium, it will be the case that the effort levels will be the same. In the equilibrium, the effort level of agent J is equal to the effort level of agent K, which is equal to m star. So let's derive the first order condition for utility maximum. This is a utility function which we have seen before. And now we have to think about what is under control of the athlete. Under control of the athlete is, of course, the effort level, and therefore we have to differentiate the utility function with respect to the effort level. Then we get, when we differentiate like p with respect to m, then of course we get this function g here. So this is the first part. We multiply through by the spread, and then we have another function here which depends on m, and this is the marginal cost of excelling effort. This has to be equal to 0. So the first order condition for each player then says that the marginal cost of effort must be equal to the spread of the prices times the height of the density function, like at the value where mj minus mk is equal to 0, like because of the fact that the two players are symmetric, they will excel like the same amount of effort in the equilibrium. And hence what is important is like how large is the density function in this point. When we put the marginal cost on the right hand side, then we are arriving this optimality condition here in equation 14. Hence, it is the case that the optimal effort is related to the spread and the distribution of efforts. So the optimal effort does not depend on the sum of the prices, W1 plus W2, which is called like the purse. The sum of the prices is irrelevant with respect to the optimal effort. But the purse will be important in the next step, because we have to clarify the participation constraint. So we have to clarify whether the agents will join the tournament. Let's have a look at scenario A, where prize money for the first place is equal to 50, prize money for the second place is equal to 10, and the spread is equal to 40. In the second scenario, it will be the case that the spread is also equal to 40, but the sum of prize money, is higher. Then let's have a look at scenario C. Also in scenario C, the spread is equal to 40, but the prize money is a -10 for the first place and a -50 for the second place. So it is a case that the two athletes have to pay in order to compete. And of course, in this situation, the sportsman will not line up. So you will not get the good athletes from Ethiopia or the good athletes from Kenya for a marathon, because they would not show up at the starting line. Therefore, you can anticipate that the purse, like the sum of the prize money, is important in the participation constraint, whether the good athletes will show up, yes or no. Of course, in a marathon, frequently the amateur runners, they are paying in order to participate, but this is not what we are looking for. Like, we are looking at two professional athletes which are running the marathon. So the purse determines whether the worker will play the game, whether he shows up at the starting line. In the principal agent literature, this is called participation constraint. And since both workers excel the same amount of effort, and also the assumption about the error structure, it is the case that the equilibrium will be symmetric. So each worker will win the tournament with a 50% chance, and a worker will only join the competition if the revenues are larger than the cost. Like, if the utility for the sportsman is like not negative. So like the revenues are given by like 50% of the sum of the prize money, 50% of the purse, because with a 50% likelihood, athlete J will be like the first one, and with a 50% probability, agent J will be the second one. So this is like the revenue, and then we have to subtract the cost, and this should be larger or equal to 0. This is our participation constraint. Now we have to go back to the firm, and the firm has to do two different computations. Let's start with the first one. So the workers, they optimize subject to the constraints imposed on them by the firm. The firm is in control of the purse and the spread of the prize money. And in the setting, the firm will adjust these two variables in order to maximize profits. However, it is a case that the competition will, in the end, like limit the firm in the dimension of both the purse and the spread. So the output of the firm is on average given by the sum of the two efforts of J and K, and this output can be sold at the price of V to the spectator. So the firm's profits is defined as revenues minus cost. So in the first part, like, we have the revenues, which stems from selling the effort to the spectators, and then the cost. This is like the prize money for the winner and the second place. When we take the expectations, then the expected value of the epsilon is equal to 0. Then we get to equation number 17. We are assuming that the firms operate in the market structure of perfect competition. And this very intense competition drives profits to zero. So the zero profit condition is that in the end, pi has to be equal to zero. Why is that? Yeah, because there are a lot of marathons in the world. So you can participate in the New York marathon, or there is a marathon in Boston, in London, in Tokyo, or in Berlin. So it will be the case that all these different places, all these different firms, which are organizing the marathon, they have to compete against each other. And this very intense competition leads to a situation where, in the end, expected profit is equal to zero. Then, when we set the profit equal to zero, we end up at this equation 18, where we have cost on the left-hand side and the revenues on the right-hand side. And since the effort levels are identical, we can also write the right-hand side as follows, like W1 plus W2 is equal to like 2 times the optimal effort level times V. Let's have a look at the second thing the firm has to do. So the firm also has to make the right choice in terms of the spread of the price money to achieve zero profits. The wrong choice means that the firm would experience losses. Competition limits the behavior of the firm, and in order to attract workers, the firm has to offer a spread for any given sum of the price money, which will maximize workers' return. Thus, the firm's behavior has to be aligned with the workers' interest by competition. The firm will choose the spread in a way that maximizes expected earnings to the worker. So we have to think about a second condition here. And we once more start with the utility function for like the worker. With a 50% probability, we will end up on the first place. With a 50% on the second place, we have to subtract the cost. Then we can write 0.5 out of brackets. We end up at equation 20. But we have seen this kind of stuff before, like we have seen the zero profit condition, like W1 plus W2 is equal to 2m star times V. When we put the 2 on the other hand side of the equation, then we end up at this relationship here, and we can insert mv instead of like this part here. So we are inserting the zero profit condition, which stems from the profit function of the firm, into the utility function, and we arrive here. Now, the firm has to maximize the utility function of the two athletes with respect to the spread. So the spread is under control of the firm, right? But the firm has to find like the right spread to incentivize like the workers. Therefore, like the firm is maximizing the utility function with respect to the spread, and we get like this effort level will depend on the spread. So we get V times del M del spread, and then we get minus del C del effort times del effort del spread. This has to be equal to 0. There is this fraction here which pops up 2 times, so we can write it out of brackets, and we get here we have the fraction which is written out of brackets. We have in brackets V times V minus del C del M in brackets times this fraction here has to be equal to 0. like this fraction is always positive. When the spread is getting larger, the effort level will be higher. So it is the case that the first term in brackets has to be equal to 0. So V minus del C dm has to be equal to 0. So V has to be equal to the marginal cost of the athlete. And we have seen this condition before. Like in the piece rate scenario, we have seen this relationship before. So therefore, Lazear and Rosen can also show that this scenario here is efficient. Let's sum up. We have 3 equations and also like 3 unknowns. So this relationship here stems from the utility function of the athletes, which was maximized with respect to m. Then this relationship here represents the 0 profit condition for the firms. And this equation was derived in the last minute. So this relationship depends or stems from the utility function, which was differentiated with respect to the spread. Now I would like to use a numerical example to highlight like this outcome. We are assuming that V is equal to 15, so the spectators are willing to pay the amount of 15 per unit of effort level. Then we are assuming that the height of the probability function is given by 0.5 and the cost function is given by C is equal to m to the power of 1.5. In the first step, I want to compute the optimal effort level. And this stems like from the third equation here. So we have to differentiate the cost function with respect to m, like we get this kind of stuff here, which has to be equal to v. And now we can solve this relationship for like m. So we put 1.5 on the other hand side of the equation, pops up in the denominator, and then we are squaring both hand sides of the equation. So then we know that m is equal to, like v is equal to 15. 15 divided by 1.5, this is equal to 10. 10 to the power of 2, which is equal to like 100. In the second step, we can use like the 0 profit condition in order to compute like the purse. So we know that we have 2 athletes. Athletes are excelling the effort level of 100. So we get 200 in effort, and we can sell like 1 unit of effort at the price of 15 to the spectators. So the purse will be equal to 3,000. The company is generating 3,000 in revenues, which can be distributed like to the 2 athletes. Step number 3, we can use the utility maximization condition of the worker in order to compute the spread. So in the first step, we put G on the other hand side of the equation, and then we know like how the spread looks like. So this is like the first derivative of the cost function with respect to m, and we are inserting like the optimal effort level that m is equal to 100. And g, this is equal to the height of the probability function, and which is equal to 0.5. So we get here the square root of 100 is equal to 10. So the numerator is equal to 15 divided by 0.5. So the spread has to be equal to 30. Now we can use the information that we know the purse and we know the spread in order to compute W1 and W2. So in the first step, we are putting W2 on the right-hand side of the equation. We get to this relationship here, and then we can insert 30 plus W2 instead of W1 here, which is performed here. So 30 plus W2, this is W1. So we can put the 30 on the other hand side of the equation. We get 3000 minus 30, and we have two W's here. So W2 will be equal to like 1485. So we know that W1 is equal to 1515, and we have solved the whole like a numerical example. We can also ask like some follow-up questions. For example, we could ask like, is the participation constraint met? Yes or no? Yes at the margin. So like the revenues to the athletes is equal to the cost, or revenues are larger than the cost, or no, because the costs are larger than the revenues. When we plug in the numbers we have in our numerical example, then it's a case that the expected revenues are equal to like 1/2 of the purse, so 1500, but the costs are only equal like to 100 to the power of 1.5, which is equal to 1000. So 1500 is larger than 1000, so it's a case that the second answer is right. For the athlete, the revenues are larger than the cost. There is one mistake here on the slide, which I see right now. There is a large M here. This doesn't make sense. It has to be like a small m. Then we can also ask, what about the profit of the firm? How large is the profit of the firm? 0, positive or negative? Of course, it's 0 because of the fact that this was our 0 profit condition. The revenues are equal to like 2 times the effort, which can be sold at the price of 15. And then we subtract the prize money. So the expected profit to the firm like is equal to 0. Like these are once more the references: Lazear, Rosen, rank and order tournament, an optimal labor contract, Journal of Political Economy, like the famous 1981 Lazear and Rosen paper, and then the teaching note of Maloney. This is the end of this video. I'll correct the mistake which appeared on the last slide, and then I'll also put my slides online so that you can always have access to my slides. Please comment in case that you have questions, in case that you detect further mistakes. Please comment. It was a pleasure to give this lecture. Have a nice day. Bye-bye.